Good afternoon, everyone.
Good afternoon, sir.
Okay. So, to the last class, do you have any doubt, anyone?
Cool, sir.
Any confusion up to the last class? No? Huh? Class list, class list. So, okay, so I hope my screen is visible. Yes, sir.
Yes, sir.
Okay. So, up to the last class, do you have any doubt, anyone? I hope no. Okay. So in the last class, basically we were discussing a problem related to cam profile design. Okay. So there, if I just for your sake of just profile of the cam operating a knife edge follower having a lift of 30 mm. So the cam raises the follower with SHM for 150 degree of the rotation followed by a period of 1260 degree. Okay, and then the follower descends for the next 100 degree rotation of the cam with uniform velocity and again followed by a dual period. Okay, so it is being said that the 20 rpm and it has a least radius of 20 millimeter. So you have to find out the maximum velocity and acceleration of the follower during the lift and as well as the return stroke, as well as we have to basically draw the profile of the cam. Okay, so now for the there first thing is like drawing the profile of the cam that is there and finding out the maximum velocity and acceleration of the follower. Out from the question we have extracted the data related to like what is the lift, what is the speed of our velocity of cam rotation, okay, and what is the minimum size, that is the least radius of the cam, okay, then all the angles like the ascent stroke angle, the first dwell, okay, then the descent stroke angle, those things, and the second last dwell, those angles we have found out. Okay, and then we have seen that basically there are two two major stages this was for drawing the cam profile. First one is what? First one, what is the first step? Sorry. First step is drawing the what? Do you recall? First is draw the displacement diagram. Okay. So as per whatever is the as per given scheme of motion. Okay. So that thing here we have already found out like polar rise stroke is with SHM, okay, for 150 degree, and then we have got the dual and the descent stroke that is for next 100 degree rotation of the cam with uniform velocity. Okay, so those things, this particular thing already we have completed, and next part is by taking data from the displacement diagram. Okay, and also we are going to take the data from the displacement diagram, that is the displacement data that we are going to utilize, and considering kinematic inversion. Okay, and considering kinematic inversion, we are basically going to first draw the cam profile. Okay, so these are the two main things. So for the first part, is there any confusion already? From here, we have already completed up to drawing the displacement diagram. That is the first part. Is there any confusion? Just let me know. Okay, so this we have completed this displacement diagram, right? So there you can see this ascent stroke is with SHM, right? And descent, then we have got the dual, okay, your uniform velocity. Okay, so I hope after the displacement diagram there should not be any problem. Now, say in the question nothing is being specified whether it's like offset type of follower or inline or radial type of follower. So cam and follower arrangement. So we'll be just be considering like it is a inline or radial type of cam and follower arrangement for our ease of understanding. Along with that, is had it been like offset type, then already some offset distance would have been provided. Right now that is also not provided, so that we'll consider. Now, next thing in the second step, okay, second stage is like we are going to basically draw the cam profile. Okay, so that is the second stage, and in the second stage what we are going to do, so for doing the second stage, first stage has to be proper, that is scale, that is important. Okay, whatever scale you consider, as per that basically while you are going to draw the cam profile, that size of that cam profile also will be dependent on that what is the scale that you have considered in that particular displacement diagram. Now, what we have to do, we have to be careful. Right now this is a what type of follower is given, this is knife edge follower given. So for knife edge follower we already know the trace point is directly located at the edge of knife edge itself. Okay, so had it been roller follower, the type of drawing the cam profile, okay, the way we draw the cam profile would have been somewhat different. Okay, so now what we will do, so already the least radius of the circle cam radius that has been already provided. So now considering that radius, okay, that is the RC value. Okay, so that least radius, considering the RC value, okay, that is already given. Okay, so it is given as how much, let's see, this radius is given as 20 mm. So 20 mm, considering 20 mm as the radius, we are going to draw a circle. So this is the circle. Okay, this circle is the circle. If you complete this circle, whatever I have marked with red mark, okay, this circle is the circle, okay, taking which have been drawn at center at O and radius equal to RC, that is the least radius of the cam. Now this basically circle represents the base circle. Okay, that is, it gives you the indication about the size of that particular cam. Okay, and cam profile is nothing but the actual working surface of the cam. It gives you the what is the look of that particular cam. Okay, so now in that case we already said some assumption you have to write down. Okay, so whatever assumption we had, so those things you have to write down. Okay, so what are the assumptions here? Basically we go for what? Kinematic inversion, right? So assumptions you have to write. Okay, so in that case what are the assumption? Basically what assumption is like, if previously cab is rotating at that particular clockwise direction, in the in this case what we consider as if cab is stationary and the follower is rotating around the cab. Okay, and direction of rotation will be reverse. Reverse means now you have to consider it is rotating in the anti-clockwise direction. Apart from that, another assumption is your assumption related to like what is the scale, etc., that you are considering for drawing that. Okay, right now 20 mm, it's a depending on what is the size of that particular page that is available with you. Okay, you take a judicial call. Okay, now directly we can go for 1:1 kind of scale, so that is up to you. So scale also you mentioned. Okay, and next, the radius of that particular circle that you have to, in the assumption itself you have to clarify. So here it is equal to RC. RC equal to the 20 mm that is given. Okay, so now this circle you have to do. So all of you are requested to draw alongside me so that you can get a clear idea about how to draw it. All of you are following me? Just let me know. Yes?
Yes, sir.
Okay, thank you. So now we'll also assume that the cam is rotating, right? Okay, and the follower is remains in this particular vertical direction. That is, this is the starting point. We will consider like that. Okay, we are not going to show the follower here or like that. Okay, we will assume the follower is in vertical direction. Okay, and it is now rotating in the anti-clockwise direction or counterclockwise direction. Now consider, so now this is a reciprocating type of follower, right? Okay, so this is knife edge type and it is kind of reciprocating type, that all of you can understand. Okay, so now what we'll do, so what is this? So if I think, so basically, it passes through the center of rotation of the cam. That means this is the inline or radial type of cam and follower arrangement. Okay. Now, what we will do? So now, considering this vertical position of the base position or the reference, we are going to, in this particular circle, circle is already drawn. In the circle, we are going to mark the different angles. And what are those different angles? That theta A, that is your ascent stroke angle. Okay. And dual. Okay. First dual, okay, d del 1, okay, then the theta, the descent stroke angle, so this is theta. Sorry, I think this laptop is somewhat difficult without the mouse. Okay, and the next way, that is the second del. Okay, so this using protector we are going to mark it. Okay, so now this angle is theta a, that is ascent stroke angle, this much. Okay, so this is, I think, how much it is given. Theta A was how much? 150 degree. Next delta I have first delta, this is first del 60 degree, next 100 degree and 50 degree. Okay, so now the next 60 degree here. Okay, so this is the first del. Now from here, this is the 100 degree. From you have to use your protector. Okay, the geometrical instrument you have to use, and automatically this will become the second delta. Okay, so this is theta A, and stroke angle. Okay, this angle is how much? This angle is 12 angle delta 1. Next, this 100 degrees the recent stroke angle. Okay, and the rest automatically becomes the second delta. Up to this much, all of you are following me, I hope. I hope yes. Okay, so next thing is now with respect to the displacement diagram, you have to consider. Now in the displacement diagram, how many divisions you have done in the your ascent stroke as well as in the descent stroke, those things you have to see. So right now in the displacement diagram, in the ascent stroke, we have considered 6 divisions, 6 equal. Particular 150 degree, we are going to divide it into 6. We are going to make it 6 equal division. Okay, so 150 divided by 6, whatever angle it comes, so that way in the using the protector you are going to make 6 division here. Okay, so suppose and so mark those division, whatever nomenclature you have utilized here. Suppose first division 1 2 3 4 5 6 like that you have done. No? Okay, so here also this 1, then 2, okay, 3 4 5 and 6, this way you're. So now in the essence stroke we are going to do the, we are going to define. Okay, so 6 equal space division. After that, this is the dual we have, and in the dual we don't have to make any division. So there we didn't have any division, so we are also not going to make any division. Next, we have got here the theta d. Okay, that is the descent stroke angle. So now coming back to your displacement diagram. So how many divisions you have made? You just see. So 6 division we have made here. So here also we are going to make 6 division. Okay, 6 equal space divisions. So it was 100 degrees, so using a protector 100 by 6, so that way, so 6 division you are going to do. And this the name, whatever nomenclature you have already utilized, it starts from 6 6 7 8 9 10 11 12 like that. So whatever division marking you use in the displacement diagram, so it should be the corresponding one. Okay, and after that there is once again the dual is there, we don't have to make any division. Up to this much, all of you are following me, let me know. whatever division we have make here in the linear scale. So same division that is in the essence stroke, here also six division, here also in the circular circle we have got six division, equal space division. Okay, so now what we'll see, so now in this, if you come back to the displacement diagram, so at position 1 2 3 4 5 and 6, so this 1 dash, those vertical lines, and similarly 2 dash, okay, don't mind my drawing, 3 dash, okay, 4 dash, etc. So those are nothing but the leaf or the displacement of the follower at that particular interval, right? So now this corresponds to this particular 1 2 3 4 5 6, those division here in this second figure, that is the cam profile figure. This corresponds to this division, corresponds to those divisions only. Okay, and now what we'll do now, using your scale, this 1 dash, whatever is this particular distance, okay, and similarly 2 dash, 3 dash, etc. Okay, so this distance you are going to measure using your scale, and that mass, suppose in the first division it is 1 dash. Okay, so now coming back to your second diagram, that is the cam profile construction diagram. So from the first division we are going to produce that mass amount, that is 1 dash, whatever we have considered from the displacement diagram, that particular distance we are going to produce in which direction, along that particular division only. Okay, similarly we are going to go back to your displacement diagram and take out that particular 2 dash, that mass distance, and we are going to extend that. Okay, we are going to extend it. Okay, how much? Up to 2 days. Okay, from 2, from this figure up to 2 days, that 2 days, and in the meantime just don't forget to give the proper name for that particular point. Okay, suppose this is the 1 dash point. Okay, similarly this mass is divided 2 dash point. Okay, similarly from 3, that will come back to your this particular diagram, displacement diagram. 3 dash, this displacement, this distance we are going to measure using scale, and that mass we are going to produce. Okay, we are going to extend, so from 3, so what will be the direction? It is not vertical or horizontal or like that, so it will be in this particular direction only, whatever we have divided. So up to 3 dash. Similar is the, like from 4 to 4 dash, 5 to 6 5 dash. Okay, 6 to 6 dash. Okay, so this division we have done. So this is for your, which one? This is done for which angle? Essence stroke angle. Now comes the leaf. Now, not leaf, sorry. Okay, now comes the first duel. Okay, now during duel, what happens? There is no motion of that particular follower. Okay, and if you go back to that particular displacement diagram, then throughout the leaf, actually, the position remains here. That means this is the displacement. Okay, so from 6 to 6 is the same thing. Okay, this here and this distance here is the same. It is at the end of the essence stroke, whatever is the leaf, at the end of first there also, the follower is remaining there, that much is the lift only. Okay, so you don't have to calculate once again 6 dash, it will be the same value. So now at the end of the duel, that is this here, the duel ends, or you can say at the start of the ending of the duel itself is the starting of your descent stroke. Okay, so you will extend up this much. Okay, 660. Similarly, just like in the we have done in the case of your ascent stroke, now this 7 dash this distance, similarly this 8 dash this distance. Okay, 9 dash. Okay, so similarly up to this much, those corresponding distances we are going to take from the displacement diagram, and that much we are going to produce in the, while constructing the campus. So from the 7 divisions, the 7 dash, from 8 division, this is the, by taking the distance from your displacement diagram, that much we are going to produce along this line, and so on. Okay, and the last one is how much? Last one is 12 and 12 days, they are the same point here only. Okay, so this ends here, we don't have to put this in. Okay, and after that there is once again that your second delta, that is the second del, that is the, your dual is there, second dual is there. So in that case, so already after 0 position the this already it has come up, so there only it will be, so there is no division to be made, and there is no extension of those line. Okay, up to this much all of you are with me. So the corresponding points you have to name, like the 6 dash. Okay, and the 7 dash, 8 dash, and so on. Okay, is that okay up to this much? have that checker. Okay. So now what does specifically this line, extended line, or you consider one dash point, two dash point, three dash point, what does they indicate? So basically these lines, okay, this indicates this much is the displacement of that particular follower up to that particular interval. Okay, so first division has got certain angle. Okay, during that case certain angle has been turned. So during that, that means this much is the lift. Okay, or you can say at, if you just point wise, if you just consider one dash point or two dash point, so that means during that particular course of movement of the cam by that much particular angle. Okay, the follower, that is, this is a knife edge type of follower, so follower assumes this particular position. That means the knife edge of that particular follower is in contact with the working surface of that particular cam at this particular one dash, two dash, three dash, etc., those points at that particular location. Understood? So now, as this is a knife edge type of follower, so already we know the trace point of that knife edge follower remains at the trace knife edge itself. So now we'll start from here. Okay. So now we know, suppose what are the location at which basically at a particular cam angular movement, what is the location of that particular knife edge of that knife edge follower. So now if we know that, and if we connect those points actually, so we can say that that particular profile, that whatever is the profile that we are going to get, whatever curve that we are going to get, that nothing but it gives you the indication about the whatever is the shape of that particular cam. Okay, because and that's why, as we have said, that the number or the more is the division that you make, the better will be the curvature of that particular profile that you get. Okay, so that will be the accuracy will be greater in that particular case. But we have time limitation, so we'll not be able to go for so many divisions. So we have taken a judicial call, like 6 division minimum that will go for. You can also go for 8 or 10 division. Okay, so depending on if the angle is very large angle, then the number of division that you will also be making will be somewhat more. Okay, if the angle where you have to make the divisions is like very small, then correspondingly you can go for C division or so. Okay, up to this much all of you have understood? Hermiki, Nilutpal?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
Rishikesh, not understood
Yes, sir.
up to this much? Okay.
Yes, sir.
Okay, so now what we have to do, we are going to suppose this O dash point, whatever is the initial point of that. Okay, and all those extended point, okay, that a 1 dash, 2 dash, 3 dash, we are going to join them with a freehand curve. Okay, so 1 dash, 2 dash, starting from the original initial position of the your knife edge follower, this is the O dash position. Okay, so we are going to join with a figure. Okay, so up to this much, this is about, this is the essence stroke. Okay, so now what about, see, there is no division in that particular dual. Okay, from 6 dash, this 6 dash to this particular 6 dash, this is the dual that we have. Okay, but there is no division, there is no division. So how we can get that particular, suppose curve profile. So in that case, we know dual is like the constant radius curvature whenever we encounter, then actually we have got that. Okay, now what you can do, considering this particular from O to 6 dash, this particular distance, you can draw a constant radius curvature. Okay, using your, okay, so now throughout, that means whenever it is a constant radius curvature is encountered, basically there is no motion of that particular. Understood this logic? Dual is constant radius curvature. Okay, that's why this distance and this particular distance is same. Next it comes the descent stroke. Okay, so now for the descent stroke, once again, just see the 7 is already, those points are extended points are already there. So it has smooth curve. Okay, you are going to smooth through and curve into. Okay, now up to this much it completes. Suppose SN, once again, this is the constant radius curve, so just darken this. Okay, don't forget to darken it, so it completes the whole profile. Okay, and this particular line is, this particular profile is nothing but the required cam profile. Okay, this is the required cam profile. Okay, so this is how you have to draw the cam profile as per given question. Understood? Yes or no? Let me know. Okay, so this is how you have to draw the campus. So what are the basic steps? First step, you have to go to the question and find out all the given data. You have to check what are the given angles, etc. Ascent stroke angle, dual, descent stroke angle, etc. And what kind of scheme of motion is there in that particular case. Sometimes it may so happen that the ascent stroke and descent stroke they are taking place with different motion. Okay, just like in this particular case, ascent stroke with SHM, descent stroke is with uniform velocity. Okay, and after that taking all those a proper scale and all. Okay, you have to, and you have to mention the scale also by using proper scale. You have to draw the displacement diagram. Okay, so first is displacement diagram. Okay, first displacement diagram. Next you have to do the assumption, that is the kinematic inversion and all. Okay, and using proper scale. Okay, and taking the least radius of the cam depending on whether it's a knife edge type of follower or the roller follower that we are talking about. You have to draw that particular cam profile. So for drawing the cam profile, this proper displacement diagram is a must. Okay, so we are going to refer the distances from the displacement diagram itself, and after that, depending on how many divisions you have made in the displacement diagram for the ascent stroke, etc., for the ascent stroke, descent stroke, so similarly you are going to make the divisions here in the circle. Okay, and after that, as it is kind of like next this many divisions we are going to do here, right? Okay, and this extension line we are going to take from the displacement diagram. So if in the first division, second division, etc., whatever is the displacement, corresponding displacement, that is the 1 dash, 2 dash, etc. So that much we are going to measure from the displacement diagram, and that much we are going to extend in that particular division also. Okay, understood. And after that, like we'll be doing this for ascent as well as descent stroke, and after that, from the knife edge, starting from the knife edge, okay, we have got those 1 dash, 2 dash, all those points. Okay, with a smooth curve, basically we are going to connect them. Okay, and that gives you the required cam profile for this cam with knife edge type of follow. Okay, so this is what has been done. And after that, as per the question, they are asking about you the velocity and acceleration during ascent stroke and the during descent stroke. So that can, for that it's easy. You just have to remember the expression for that, and directly you can. Okay. So during ascent, just be careful. That means you have to consider the corresponding angles, ascent stroke angle. During descent, similar expressions will be valid, but you have to consider the descent stroke angle. Okay. So now, what is the Vmax expression that we have? We know that Vmax is h by 2. For this particular case, what type of motion we have? It is the SHM motion. Okay. So for maximum velocity, you already have this particular expression. Maximum velocity equal to f by 2 equal into pi omega divided by Sn stroking. Okay, so now here omega is required. That's why we are going to find out the omega. N is already given. Omega can be found out like 2 pi n by 60. Just by putting that value, we have obtained omega to be 12.5 second radian per second. Okay, so that omega value we can put in this expression for Vmax. Okay, so now h is already given. The lift is 30. So we are putting it like 30 by 2. Pi is already known. Okay, pi into this omega is 12.57. Just now we have found out. And be careful, these angles theta and all, okay, these are given in terms of your uh, degree, but here you have to utilize it in radian. Okay, so 150 degree, just convert it to corresponding radian value by multiplying it with pi by 180. So you will get the corresponding angle in radian. Okay, so that you have to utilize. So after that, just by simplification, we have obtained maximum velocity to be 226.3 mm per second. So as we are utilizing h value in millimeter, that's why we are getting this in millimeter per second. Okay, so that's about velocity, maximum velocity. Similarly, by referring to the previous knowledge, okay, you can also get the expression for maximum acceleration for SHM stroke. Okay, So now that is h by 2 or into pi omega divided by theta a whole square. Okay. So once again omega is already known, h is already there, and once again the theta a, that is your stroke angle, has to be utilized in to be converted into radian. Okay. So just by putting those value and simplifying, we have obtained the acceleration to be 3.413 meter per second square. That is about ascent stroke. Similarly, we have got for descent. Okay, for descent stroke also you need to find out, but descent stroke is not with ascent sum, it is with at uniform velocity, so expressions will be different. So P max is already we know h omega by, and now this angle is theta d. Okay, that is the descent stroke angle. So once again omega is already found out, and this theta d has to be considered in terms of radians. Okay, so that is the case. Okay, and the maximum acceleration, and it is 0 because that is uniform velocity that we are talking about. So there is no question of having any acceleration. So maximum value of acceleration itself is 0. Okay, understood? So this completes this particular problem. If you have any question, you can ask. If you have understood, let me know. Then it will be easy for me to go to the next question. All of you are following me? You are trying along with me? You have drawn, right? At least maybe a rough drawing also, but you have drawn, right? Teja,
Yes, sir.
Arsisman, what about Arsisman? Arsisman, you are here? Seems like he has just joined. Nohosol?
Yes, sir.
So all of you have understood, right? Okay,
Yes, sir.
thank you.
Yes.
Okay, so then we can go for another problem. So here in the previous case, we have considered the inline cam and follower arrangement. Okay, now we'll go for a offset type. We'll see how to draw the cam profile, how to construct cam profile for offset type. Okay, and in the previous case, we have gone for which type of follower? We have gone for reciprocating knife edge reciprocating follower. Okay, now once here we'll be going for one roller follower. We'll see how for roller follower we have to draw the or construct the cam profile. Okay, so now what does the problem statement says? So it says that the following data relate to a cam profile in which the follower moves with uniform acceleration and deceleration during ascent and descent. Okay, so in the means in both the case it is uniform acceleration retardation scheme for ascent and descent. Okay, so minimum radius of cam that is given, so you'll find out the given data minimum radius of cam r is equal to 25 mm. Then the roller radius is given 7.5 millimeter. So r, so that means if roller radius is given, automatically we understand what type of roller follower it is, or like it is there. Okay, so we have got roller follower. That the lift of the follower given, so 28 mm. So it is given as 28 mm lift. Okay, then the offset of the follower axis is given, which is 12 mm towards the right hand side. So now whenever offset of the follower axis it is given, automatically we understand that it is a we are talking about offset type. Okay, not a inline type. Okay, so that means the way we have to construct the cam profile will be somewhat different than that of the way we have drawn the cam profile for your inline or radial type. Okay, now the other angles are given. So ascent stroke angles is given 60 degree, theta d, theta 8, 60 degree. Angle of descent, that is theta d, is given as 90 degree. Okay. The angle between angle of dwell between ascent and descent, that is the first delta. Okay, the L1 is given as 45 degree. Automatically we can obtain the second delta, that is by doing 360 degree minus these angles. Okay, we get it to be 165 degree. Okay, and speed of rotation of the cam 200 rpm, n is given, n equal to 200 rpm. Okay, so these are the given data. What you need to do, you have to draw the profile of the cam, that is you have to construct the cam profile and also determine the maximum velocity and uniform acceleration of the follower during the outstroke and the return stroke. Okay, so now for finding out this, okay, numerically you can find out, we already have the known expression for that, so directly it can be used. So main thing the main thing to know is how to draw the cam profile for this kind of case. Okay, so now here what you'll do whenever you write about theta a and theta d, so just along with that you always mention what type of motion is there. Okay, so this is which is uniform acceleration and deceleration in both the cases. Okay, so just in bracket you just mention here, okay, for theta as well as for theta d, so that later on you don't get confused. Okay, so what kind of motion you have to draw, because the camp construction of displacement diagram for different types of movement, the way you have to construct is different. Okay, for acid semi it is different, for uniform velocity it is different, for uniform acceleration and retardation scheme also it is different. But right now here one thing is good, like in the previous problem put the movements for ascent stroke as well as descent stroke, they were different, but now here it is both of them are same. Now this is offset type. Okay, so this is offset type, just remember this is not previous one was okay anyway. And what is the offset distance? 12 mm towards right. Okay, so now towards right means that means if you consider the base circle, so from there in the right hand side direction that offset is there. Okay, so let's consider suppose the case, suppose this is the cam. Okay, we don't know what is the right now what is the considered. Okay, now from this this is that means it is sorry, so the follower is somewhere here. The roller follower, it is roller follower, so it will not be embedded within. Okay, so don't like okay, so this is the cam rotation. Okay, so the circle will be here. It is not embedded, don't worry, it should be a link in the surface of the okay, don't mind my drawing. Okay, so this is that means 12 mm. This electricity is 12 mm. Okay, so this is what is the meaning. Okay, so now how to draw? So first step will be definitely drawing the displacement diagram as per proper skill. Second step is drawing the cam profile. Okay, so it is the same. Now for drawing the displacement diagram, what are the stages involved? So first you have to utilize the proper scale. So utilizing proper scale, okay, to, or I can stroke for x-axis and y-axis. Sorry, scale is important, proper scale is important, you have to mention it. Okay, so after that what we are going to do, we are going to, as per scale, we are going to draw the displacement diagram. Okay, first step drawing the displacement. So for that what we do, this horizontal line we have along the x-axis, we consider the cam angular motion movement, that is ultimately those angles, ascent stroke angle, dual descent stroke angle, etc. Along y-axis we consider the lift of the follower. Okay, and this is as per scale. Okay, and we complete this particular angle. Okay, and as per scale, if this is ascent stroke angle, okay, this is theta a. Okay, so as per okay, this much will draw, and we are going to make equally spaced even number division. We are considering 6 division. Okay, so 6 division like this, and on so on. Next is the here to here as per scale. We will mark it. Okay, it is the first delta. Okay, and from here to here, this is the what, this is true. As per scale, whatever is the distance, that way you have to mark. Okay, theta d. Okay, And we know how to draw the, you can say, displacement diagram in the case of uniform acceleration and uniform reduction. Okay, so what we'll do, six division we have made, so middle one we'll consider, so vertically equally like space six division will do. Okay, and half of it will draw from this side. Okay, and other half we are going to draw from that side. Okay, and just like in the previous cases we have discussed. Okay, so we are going to join that o with this a dash, 2 dash, 3 dash, like that. Okay, so first line o with 1 dash. Okay, up to this one. Okay, this division, first division, so wherever they meet this first vertical and the first line, this is the 1 dash point. Similarly, while drawing this particular inclined line, joining this particular inclined line, so wherever the second vertical meets with the second line, that is the 2 dash point. Similar case with 3 dash. Okay, and while coming from this side, 4 dash, 5 dash, and 6 dash will get here. Okay, and for dual, there is no division that need to be made. So what will happen? So after drawing the smooth curve, we have obtained the curve to be something like this. Okay, now that means 6 dash is the position where my this particular follower lies at the end of which particular stroke. This is the ascent stroke. Okay, and now starts the 12. Now that means the position of the leaf follower itself is here, it is right now at 6th position, so it will remain here, there will not be any displacement. Okay, so now throughout the leaf, so you can darken it throughout the dual, not lift. Okay, just darken it. Up to this much, all of you are with me? Let me know. I hope that answer to be a yes. There is no answer. Okay, and after that, in the similar way, you will be making for the your which stroke, descent stroke. Okay, this curvature. And don't forget to give proper name to those division as well as those points. Okay, so because these distances will be important while extending or while drawing that particular cam profile. Okay, so first step is drawing the displacement diagram, that is done. Next step is, once again we have to go for the assumption. We'll be considering the kinematic inversion. What we will write in the assumption, that means we assume that as the cam is rotating in the clockwise direction, so we assume the cam to be actually stationary and follower is rotating in the around the cam in the anti-clockwise direction. And now this particular circle, the radius of the circle that you need to draw is r equal to rc plus rr, where rc is what, the minimum radius of the cam, and plus the roller radius. Now it will come. Why it is there? Basically, we know that in that particular case of roll, as in the question, it is a roller follower that is there. Okay, so the tracing point of that particular roller. Okay, we know that it is at the center of the roller itself, and that gives you that particular indication about the circle. Okay, the base circle. Oh, that is done. Okay, so what you are going to draw, you are going to draw a circle with radius equal to rc plus rr, that will. Okay, and this particular circle is this circle. Okay, is the circle record circle. Understood? Yes, I hope that is done. Okay, now as this is a offset case. Okay, so now what we will do, considering the offset distance, we are once again going to draw a circle, concentric circle, by taking that offset value to be that particular radius of that particular circle. Okay, so we are going to draw under small concentric circle for the offset, considering the offset, this particular circle. All of you are following me? Let me know. Now what is the radius of this? Radius value of this smaller circle is equal to how much? Offset only. Okay, now if we consider any radius, okay, any radius is circle, so it's a constant radius throughout. So everywhere from the circle, the distance of that particular periphery is that particular RC only, not RC, sorry, that particular offset distance only. Okay, so now that means if I consider that particular follower which is at a particular location, it is tangential to this smaller circle, then each and every time it will be, the value will be equal to the offset value only. Okay, because this radius of the circle itself is equal to offset value. Okay, and done. Okay, so now that means if we consider the cam to be stationary, so the follower will be tangential to this particular small circle in all its position. If it is at this vertical position, so here it should be tangential. Now we are assuming that the follower is rotating around that particular cam. Okay, so now in all its position, it should be always tangential to this particular smaller circle, because it is at a this particular 12 this particular, it is 12 or 20, whatever value it is given, that is the value of that particular what the offset. Okay, so now drawing this particular tangent, vertical tangent. Okay, so initial position of that particular roller follower we are considering, so whatever is the roller value, roller radius value given, so that we will draw here. Okay, so okay, so let's consider. So now we'll join the center of this particular roller with the center of this particular circle, and this value, this line will consider as the baseline for taking the angles, different angles, that is the theta A, delta, theta D, etc. Okay, and what I'll do, so whatever is the angle, theta A, delta, etc., this circle, considering this O dash as the baseline. Okay, so we are making the angle. So this is theta A up to this much, this is theta A. Okay, then from here to here, this is your delta L1, sorry, L1. Now this angle is theta D, and automatically the rest of the angles become what the next one. Okay, so I think for today our time is almost over, so we'll be having some other classes, I think. Okay, so this portion of drawing the type profile, okay, after this how to draw, okay, that much we'll be covering in the next class. So for today, what you do, whatever up to this class we have discussed, okay, that much you follow. Okay, and in your fair copy, try to draw this displacement diagram, at least up to the displacement diagram properly. Okay, is that clear?
Yes, sir. Yes, sir.
Okay, so I'll be taking the attendance. In the next class, I'll this particular portion of cam design construction will once again discuss. Okay, don't do. So respond to your name calls. Nilutpal,
Present, sir.
Shankar,
Present, sir.
Arshisman,
Present, sir.
Rehan,
Present, sir.
Artha,
Present, sir.
Rishikesh Pasumotari,
Present, sir.
Hermiki,
Yes, sir.
Nahosal,
Yes, sir.
Heza,
Yes, sir.
Rishikesh Nath,
Yes, sir.
and Emil. Emil, absent. Okay, so if you have any question, you can ask. Otherwise, we'll meet in the next class. Up to this much, you have understood, right? Please respond, anyone. Okay. Okay, so no question it seems, so we'll stop the meeting now. Thank you everyone for joining.
Thank you,
Thank you,
sir.
sir.
Yes, sir.
Thank you,
Yes,
sir.
sir.